In this lesson, we're going to introduce the concepts of continuity and differentiability. Now, to begin with, continuity and differentiability are properties that functions can have. Let's begin by talking about continuity first, and then we'll talk about differentiability afterwards. To properly understand continuity, we're going to want to start with the graph of some function. Now, this function over here is continuous, and we say it's continuous because you can draw it without ever needing to lift your pen. So even though this function has a sharp point over here, it is still continuous. However, if you got to this point and then suddenly jumped from here to here, then this function would not be continuous. Even if the function had little holes on it, then it still wouldn't be continuous because you'd have to lift your pen when you got to those holes. Now, in order to write down a mathematical definition for continuity, we're going to need to use the concept of a limit, which was introduced in another lesson. Suppose we wanted to investigate whether this point over here was continuous. To do this, I'll start by labeling the point A. Now, if this function is going to be continuous, forget about having any gaps in the function, so that means f of a has to be defined. Now, as I said earlier, I like to imagine limits by pretending that I started somewhere on the curve and skiing towards x equals a. The height that I seem to approach is the limit that I'm looking for. So then it actually becomes pretty simple to talk about what continuity should be. If this skier over here approaches this point f of a, then we know that the function has to be continuous. In the language of limits, we'd say that as x approaches a, f of x has to approach f of a. The notation shows this as well. The limit as x approaches a of f of x just has to equal f of a for continuity. Now, using limits actually takes care of another thing that might actually be a problem if we aren't careful. Suppose we had this situation over here, where the graph just suddenly jumps from one height to another. It turns out that by this definition, this would not be considered continuous. This is because limits only exist when the limit from the left and the right are exactly the same. So while skiing in from the right actually does lead us to a value of f of a, skiing in from the left seems to just take us to this height over here, which is absolutely not the same as f of a. So this means that for a function to be continuous, a skier coming in from the right and from the left both have to reach this exact same point, which is f of a. I still find it so cool that we can actually translate a sentence like this into a mathematically precise formula that we can actually calculate with. To actually explain these ideas to you properly, let me bring out an example of a function that is continuous and one that isn't continuous, and then we'll see how these limits actually work with them. So here I've actually shown you two example functions, and we should try to figure out which of them is actually continuous. I can tell you that one of them is, and one of them isn't. To be really specific, I'd like to find out whether each one of them is actually continuous at x equals 1. So let's begin with the function on the left, and try to actually figure out what it seems to approach when x equals 1 from both directions. So when x actually approaches 1 from the left, we can say that the left-handed limit of s of x as x approaches 1 is approximately equal to s of 0.999. So if we go ahead and replace every x for a 0.999, we can see roughly what value we're approaching from the left. So we notice that when x equals 0.999, then s of x is exactly equal to 0. And this means that our left-handed limit seems to approach 0. Now, to actually approximate the limit as we come in from the right, we can choose x to be 1.001. So then we can actually repeat all of these steps, replacing 0.999 for 1.001. So this is actually pretty peculiar. We notice that the limit from the positive side is 1, but the limit from the negative side was actually 0. Because the limits from the left and the right are not the same, there's no way that this function can be continuous. In fact, this condition over here is just undefined, so there's no way that this whole condition can be satisfied. Now this is actually something that you can easily verify just by actually drawing the graph of s of x. So you can clearly see that the function jumps as soon as we get to x equals 1. In fact, there's no way that this function could have been continuous at x equals 1 at all. Because when x actually equals 1, if you tried subbing 1 into this equation, you'd actually be dividing by 0 in here, and that's obviously not allowed. However, even if we modified s of x to output 1 when we put in 1, then the function still wouldn't be continuous, because the limit from the left is just not equal to the limit from the right. However, if we actually look at v of x over here, we're going to notice that things are a little bit different for it. This time I'm actually going to start by drawing on its graph. Now this function definitely looks continuous, but we should actually verify that by looking at the left limit and right limit, and then actually showing that it's the same as the function value at x equals 1. So again, let's start with the limit on the left. The left limit is approximately going to be equal to v of 0.999. Again, we can just swap x for 0.999 and sub it into the calculator to find an approximate value for the left limit. So if you actually tried subbing in more and more 9s, you'd notice that this left limit is going to get closer and closer to the value of 0. Now we can also go ahead and find the right limit, and to do this we'll just sub in v of 1.001 as we did before. Now we can swap every x and again find the value with a calculator. Now this one's actually a little bit different. We notice that the left limit and the right limit both seem to approach a value of 0. We can also see this on the graph. The left limit goes to 0 and the right limit also seems to go to 0. Now if we actually look at our condition for continuity, it's not enough for the left limit and the right limit to be the same. We actually need both limits to actually equal f of a. In this case we've actually chosen a to equal 1, and therefore we want v of 1 to equal the limit over here. So now we can just go ahead and replace x for 1 to test that it's the same as the limits. Now as we know, 1 minus 1 is just 0, so that means v of 1 is also 0. So as we said, if we get closer and closer to 1 from the left, it seems like we're approaching 0. If we get closer and closer from the right, it still seems like we're approaching 0. And since v of 1 is exactly equal to 0, then we know that this function is actually continuous. And this actually completes our example for continuity. As you saw, continuity is actually a property of a particular position, a. Therefore, it's perfectly possible for a function like the one I'm drawing right now to be discontinuous at a, but be continuous everywhere else. Now, whilst this function over here is actually continuous, I wouldn't call it smooth because of this very sudden change in direction over here. Now, we finished discussing what it means for a function to be continuous, as you saw here, but in order to have a function that we'd call smooth, we need more than just continuity. Now, I hate to do this, but this lesson is getting a little bit long, so we'll talk about the next condition over here, which is differentiability, in another lesson. So I look forward to seeing you there where we'll continue this discussion.